Hello and welcome back to the video. Now we have completed all the basic logic gates and universal logic gate as well as special logic gates. We have also done some Boolean algebra and some examples on the Boolean algebra, uh, such as application of De Morgan's law, distributive law. Some more laws will be discussed in upcoming lectures, but now we are going to apply these gates, these universal logic gates to make basic logic gates and special logic gates. So let's see how these universal logic gates are used to make these basic logic gates and special logic gates. Logic gate designing, uh, designing using NAND gate. So we will try, we will use this NAND gate to build another gates. So first of all, NOT. So to build a NOT gate, we have to do nothing. First of all, we are making NAND gate. Okay. And this is a 2 input gate, है ना. So first we will give this X input to the NAND gate, and now we will make this connection. So this has become a NOT gate. Let verify how this is working as a NOT gate. So means we have given the X input, so X will be here and X will be here. So this will be X dot X not. Now let's simplify this. We know that X multiplied by X is equal to X, so this is nothing but X naught. So now let's see. Now we can see easily that we are giving X and we obtain this X bar. So this gate is acting as a NOT gate. Now we can also make a buffer. You can recall we have done this buffer in first lecture. To make this buffer, we have to do nothing, just first we have to make this NAND gate, then provide this input X. Now another NOT gate as a NAND. So this is our another NAND gate, and similar this. So here our input is X, so here it will be X bar, and here it will be X double bar, and we know that X double bar is nothing but X. So this is our buffer. We can also make AND gate from NAND, so let's see how this we have to make. So in AND gate we have to give 2 input, so X and Y, and this is NAND. And now we will apply a NOT gate just here. Now let's see how this is working as a AND gate. So here it will be input as X Y bar, and it is NOT gate, so it will be XY double bar, and we know that XY double bar is nothing but X, so this is X dot Y, X dot Y. So we can say that we can see that this is working as a AND gate. Now we will try to make OR gate with the help of NAND gate. So this is one NAND gate, the input will be X. This is another NAND gate which is working as NOT, and the output will be Y, and the output of these two NOT gate will be given to another NAND gate, and this will be work as OR gate. Now let's see how it is working. So this is X, and we know that this work as NOT gate, so this will be X bar, this will be Y bar, and in this gate it will be X bar dot Y bar ka whole bar, because we are giving input X bar and Y bar to this NAND gate, and it will be multiply both and take a NOT. So apply the De Morgan's law. This will be X double bar plus this will be Y double bar, and we know that X double bar and Y double bar is only X and Y. So we can see this is working as a OR gate, and to build a NOR gate, we have to do nothing, only just wait a minute. Fifth one is NOR gate. So this is OR gate. So this is our OR gate. We will add one NOT. So it will be act as NOR gate. So this is quite simple. These are basically basic gates, basic logic gates. We will try to build XOR gate with the help of this NAND gate, which is little bit of complicated, but it can be made with this NAND gate. So which was this is a sixth. So first we will take this input, which is A, or we can say X A. This one is input, which is B. Okay, and we will give it to the NAND gate. Okay, this is NAND gate, and we will take one input from here and one input from here, and we will give it to the another NAND gate, and output of this NAND gate we will give to this NAND gate and this one NAND gate, and the output of these two NAND gate will be go to the another NAND gate. Okay, and this is our XOR gate. Let's see how this is working as a XOR gate. So here is means we are providing input A, so here the input will be A, here the input will be A, here we are providing input B, so here it will be B, here it will be B, So it will be a b bar, a dot b bar. Okay, and here this output of this gate, this NAND gate is going to this output of this NAND gate is going as an input to this NAND gate. So it will be a dot b bar ka bar. Okay, and here it will be b dot b ka bar and whole bar. Okay, now simplify this expression by using De Morgan's law. So a bar plus a dot b ka double bar, it will be b bar plus a dot b double bar. Okay, this will be AB and this will be also AB. Okay, okay, now use distributive law here. So it will be a bar plus a. First we will use this and then this, a bar plus b. Okay, same use here, b bar plus a and b bar plus b. Okay, now we know that this will be 1 and this will be 1 because a bar plus a is equal to 1, b bar plus b is equal to 1. And the left part will be a bar plus b and here it will be b bar plus a, and this is going to this NAND gate. So b bar plus a and a bar plus b, this is an input to this NAND gate. Now what will be here? Here will be a bar plus b multiply by b bar plus a to the whole bar. Okay, now let's simplify this expression, this one. So first multiply this whole term. So by multiplying we will get a bar dot b bar plus a bar a plus b bar plus wait a minute, a bar b bar and a bar a, b bar and b a. So this expression, now apply bar to this. We can easily see that this part will be 0 and this part will be 0 and left part will be a bar b bar plus ab ka whole bar. Now apply De Morgan's law here. It will be a bar dot b bar. Now apply De Morgan's law here. A double bar plus b double bar, a bar plus b. This double bar will be a and b. Now multiply this, it will be a dot a bar plus a b bar plus a bar b plus b bar. These two terms are going to be 0. The left part will be a b bar plus a bar b, which is a XOR b. So this gate is acting as an XOR gate, and now from XOR we can easily make XNOR by just putting one NOT gate here. So let's make I should copy this, and this one will be 7th. And here it is a b bar plus a bar b. Now connect one NOT gate here, okay, and the output will be it will be a b bar plus a bar b ka whole bar, okay. And let's simplify it. Okay, so it will be a b bar ka whole bar dot a bar b bar ka whole bar. Apply De Morgan's law here. A bar b double bar a double bar plus b bar, and it will be b, it will be a. Now multiply. A dot a will be 0, a bar b bar plus ab, and b bar will be 0, so it is nothing but a XNOR b. So we can also easily make XNOR by these NAND gates. So basically we can make all these special logic gates and basic logic gates with the help of NAND gate. Similarly, we can also use NOR gate, which you can try yourself to build these gates. So we can stop here by conclusion, simple conclusion, that how many gates are used, how many NAND gates are used to build a particular gates. So concluding, for NOT gate we can see only one NAND gate is used. For OR, 3 NAND gate are used. For buffer, 2 NAND gate were used. For NOR, it was 4. For XOR, sorry, let first we see a NOR, and after this and no, NAND, actually NAND is itself NAND, so 1, and for AND it was 2, and for XOR it was 4, and for XNOR it was 5. So from here we can see that how many NAND gates were used, number of NAND gate which were used to build these basic or special logic gates. So I think we should stop here. Next time we will come with another topic in this digital electronics. Till now, bye bye.